So, now we are stating this very important result, the Girsanov's theorem, but in the one dimensional setup, not in the multi-dimensional setup. We will not go to the multi-dimensional setup in this course, although it takes a long time. So, we will state the theorem and then we will prove it step by step. So, let Wt be a Brownian motion in the probability space and let Ft be a filtration associated with the Brownian motion. So, all these terms do come in the first part of the series. Okay. Let theta t be an adapted process, means adapted to this filtration, that is theta t is Ft measurable for each t, be an adapted process. Okay. So, we define Zt, a new process given as follows: exponential you could feel that it is almost the type of thing that we wrote for the normal distribution, essentially related to essentially related with geometric Brownian motion. So, let us not. So, we define this and we also defined a new process from the Brownian motion, which is given by Wt plus addition of the integral So, we essentially have to show that this is a Brownian motion. So, now we are getting we are putting a condition which guarantees the existence of an Ito integral, which will come in the proof of the theorem. See, those who have not done it, those who have not done the details, just learn the statement that okay, from an old Brownian motion you can construct a new Brownian motion, that is enough. Set Z equal to Zt. So, Zt, that the terminal random variable of the stochastic process Zt is given the name Z, by which you transfer the measure from P to P tilde. Then E of Z is equal to 1 and P tilde is given is the new measure new measure or new probability measure, I should write new probability. Obviously, here z is obviously greater than equal to 0 and all those things, because of the exponential function is actually strictly greater than 0. Probability measure given through z, given by z, and p tilde is the new probability and under, and if p tilde is the new probability measure given by z, then w tilde t is a Brownian motion under p tilde, is a Brownian motion under p tilde. So, here it is, here is the important thing, that it is a Brownian motion under p tilde. So, what are the things that we have done? We will now do the proof after rubbing this, because we have a one board system here, I do not have any other board. So, we define a process zt which will allow you to create a variable z, with which we can show that e to the power z equal to 1. And then if p tilde is the new probability measure given by z, that is integral z dp is p tilde a, and integral a z dp is p tilde a, then w tilde is a Brownian motion under p tilde. So, what it says that give me a Brownian motion under p, then I can create a new Brownian motion by certain translation and under not p but p tilde. This p tilde plays a role of risk neutral measure when we start trying to prove the theorem of Black and Scholes, the result of Black and Scholes. So, let us now rub this and then do the proof step by step. The first thing, how do I know that w tilde t is a Brownian motion? There is a very famous result of Levy which says that if Wt is a stochastic process which starts at 0, that is W0 is 0 or W tilde 0 is 0, and it is a Martingale and has a quadratic variation equal to t at any t, then that one, such a stochastic process has got to be a Brownian motion. So, this is something. So, again I repeat that the key to the proof of this result is a Levy's theorem. So, Levy's theorem states that if there is a stochastic process which starts at 0, is a Martingale, and at every time t the quadratic variation is t, then such a stochastic process has got to be a Brownian motion. Of course, I have not been very clear, I have not told it in detail. Of course, you have to say that that stochastic process must have continuous path, because Brownian motions must have continuous path. So, that is exactly we have to show. So, we will show first that w tilde starts at 0, at 0 it will be 0. Obviously, if you put 0 here, if you put 0 here, this goes to 0, w0 is a Brownian motion, so it is 0, w tilde is 0. Then you have to compute its quadratic variation and show that it is t. So, once you show that thing, then you, and of course, because of the continuity of this path, and we can easily speak about the continuity, because of the continuity of this path and this integral as a function of t, assuming that theta is adapted process is a continuous function, that this would result in a continuous function, right. As a function of t, it will be continuous. So, ultimately this will be a continuous function, right. So, every sample path would be continuous. So, what would be now that we have to show that quadratic variation is dt, and then you have to show the wt tilde t is a martingale. So, the whole machinery of the proof, or all the things that we have developed in the last lecture, is to show that w tilde t is a martingale. So, now we will remove this proof and remove this statement and then write down the proof. Okay. Now, for the proof, w tilde 0 is 0 by definition. W tilde t is continuous. If we take theta t to be continuous, it's, and we are taking it to be continuous. Without it does not matter, it is better to have continuous function. But even if it is a Lebesgue integrable function by the is a measurable function by the first fundamental theorem of integral calculus, Lebesgue's calculus, you can show that the function in t is continuous. So, whatever it is does not matter. You can think that theta is continuous, nice function. Now, if you look at this, the expression of w tilde t is wt plus something. In shorthand, we can write, that is in the SDE form, stochastic differential equation form, we can write this as theta t dt. So, if you want to compute the quadratic variation, let us just compute this. These are the tricks we have learned in the last previous part. So, it will become wt plus dwt plus theta t dt into dwt plus theta t dt. Finally, if you have this will be dwt theta t dwt dt plus theta t dwt dt plus theta square t dt dt. So, all this is 0. So, second variation of a normal function is 0, these cross variations are all 0, which we have learnt, and this is dt. And this shows basically so continuity that, so w starts with 0, w is continuous, w has a second variation t at every t. So, what we have to just prove is that the fact that w tilde t is a martingale, and then you see the analysis now starts. So, we will first show that zt is a martingale. So, step 1, zt, the process that we have defined, is a martingale. Of course, you might say that why you are having the zt. That would need further more details, which we would not like to give in this course, as why you have chosen zt. The choice of zt is pretty important. Why you are always choosing exponential function, obviously to keep it positive, but why this sort of choice? This essentially comes from the certain structure of the stochastic differential equations that is used in case of the stock prices, the geometric Brownian motion. So, once we start doing more about that, you will get a feeling why it is coming like that. So, so xt we write as xt is equal to what was written inside, that is minus 0 to t theta u dwu minus half 0 to t theta square u du. So, now write fx is equal to e to the power x. So, f dash x is equal to e to the power x and f double dash x is equal to e to the power x. Now, d of zt is d of f of xt. Now, we can apply the Ito's formula, and by Ito's formula we have this to be nothing but f dash xt dxt plus half f double dash t dxt which is the quadratic variation. So, this is by Ito's formula. Okay. Now, you know what dxt is. So, what is dxt here? Dxt x0 is 0. So, dxt is minus theta t dwt minus half theta square t dt. This is your dxt. So, I would ask you to find the quadratic variations yourself. Just to try it out, I am writing down the answer. Always use shorthands. So, whenever you have the Ito integral, you can write them in the form of stochastic differential equations. So, I would ask you to, so this can be written as so e to the power xt is of course zt. Plus half you find out the quadratic variation. I am not doing the detailed calculation. So, this would be a good exercise to find out the quadratic variation, and I will ask my TAs to actually put it in the assignments for you. So, once you know this, you know that this into this and this part cancels out. So, finally, what you have is that dzt is minus of theta t e to the power xt is zt into dwt. So, what you from here what you can write, if you write down it in the form of the Ito integral, zt is z0 minus integral 0 to t theta u zu dwu. This is just a constant and this is a random variable, and this is a constant, but what is this? This is an Ito integral, and every Ito integral is a Martingale. So, zt must be a Martingale. This is I am using the fact that Ito integrals are Martingales. Okay. So, that is one piece of it. So, once that is proved, now expectation of z is expectation of z of capital T. Now, because it is a Martingale, expectation at every level remains same, expectation of z of 0. So, z of 0 is 1 because it is expectation of 0. So, it is same as z of 0 is 1. Now, since zt is a Martingale, we can write z of t is exponential, expectation z of capital T f of small t. T is the largest one, largest time. So, this is because z, we have defined zt as z, and e to the power z is, when expectation z is 1. So, what does it mean? That zt is a Radon-Nikodym process. So, this implies that, so we can now apply things about lemma A and lemma B. Zt is a Radon-Nikodym process. Okay. But before doing so, we will first show that our claim would be to show that W tilde T and Zt, this process is a Martingale. Actually, when you write everything in a form of a stochastic differential equation, and if you do not have the dt term plus dt, you only have the dwt term, it becomes a Martingale, because that is just an Ito integral. So here also we are going to do something like this. So d of So if you look at Ito's product rule, so by Ito's product rule, so derivative of this into this plus derivative of this into Wt plus derivative of this into derivative of this. So not really derivative, but okay in that sense. So Ito's product, by Ito's product rule, we have dZt plus Zt dWt plus dWt dZt. This is by Ito's product rule. So you write down what was dZt. You already knew what was dZt. So if you write down from the previous case what was dZt, then it will become minus W tilde T theta T Zt dWt plus Zt Now, if you write down dWt in detail, so it will become dWt plus theta t dt. What about this thing? This is a cross variation, and this cross variation will go to 0. You can write it down in detail and write down the cross variation, writing Zt in this, you can show that the cross variations would go to 0. So this part will now, what I will write here, I will have dWt plus theta t dt plus Zt, which was already known here, minus theta t Zt dWt. So here you see, here if you take the first term and multiply with this term, you will have dt here, but this term and this term, this will be a cross variation which will give you 0. So what is happening is, let me write it down in detail, minus Wt theta t Zt dWt plus Zt dWt plus theta t Zt dt. Now here if I multiply this one, it will become minus theta t Zt dWt is dt. Now plus theta t into this, right. So minus theta square t Zt dWt dt with cross variation will give me 0. Now this term will cancel out. So finally I will be having minus W tilde t Zt plus theta t z t, or just write theta t plus 1 into z t dwt. Now w tilde 0 is 0, so basically you can write w tilde t, so w tilde, so this, if I put 0 here, this whole thing becomes 0, z t is nothing but 0 to t minus w tilde t theta t plus 1 z t dwt, which is an Ito integral. So this is an Ito integral, this whole thing is an Ito integral, which is a Martingale. So this would imply now that this process is a Martingale. That is the beauty of mathematics actually. So once I know this, I can go back and apply my theorems, lemmas A and B. Now my job would be to apply lemma A and B and finish off with this. So we are in the final phase of the process, and we are now going to prove that W tilde t is a Martingale under the probability measure P tilde. So let us show this. We have to show that this is W tilde S. So now if I go back, then from my lemma B, because Zt is a Ft measurable random variable. If you look at the definition of Zt, it is clear that it is an Ft measurable random variable, because theta is Ft measurable. So Zt itself is Ft measurable. So I will have by lemma B, Zs is equal to exponential W tilde t Z of t Fs. So this is by lemma B. Now W tilde t and Zt we just have proved it to be a Martingale. So by the very definition of Martingale, this simply means W tilde S Zs, and that simply gives me W tilde S. That is what we have started to prove. This would imply W tilde, that W tilde t is a Martingale, and that completes the requirements of Levy's theorem, and hence the result. And as the French would say, we would write voila, that is it. Thank you. So we have completed one of the most central results that you require to study mathematical finance, and tomorrow we would go more deeper into the study of mathematical finance and move towards the Black-Scholes formula. See, a lot of details cannot be done here because of the time, otherwise there is a lot of very small details. All these things are actually almost surely, all the equalities are all in here, all the equalities, these expectations, all these equalities with expectations, they are in the almost surely setting. Thank you very much, and we will see how things proceed in our next classes. 3 more classes to go. Thank you very much.